Hello again everybody, welcome to the second video on the Stats and Mechanics chapter 1.2 for year 13. So we've had a look at how we can transform, once again from year 12 this one was, how we could transform exponential curves into straight line relations, and now we're going to have a look at how strongly these relationships correlate with one another. But instead of actually drawing a line of best fit from GCSE using a ruler and doing it by eye, I'm going to show you how your calculator can calculate the line of best fit exactly with no need for any guesswork. So there is an equation for a line of best fit, and the Classwiz will be your friend in this regard. So before that, you can probably guess there's going to be some warm-up questions, but what you might not expect is this time I've only got two for you to try. So here they are. Two big questions, as you can see, lots of parts to them. These are exam grade as well. I've taken these from an Edexcel practice paper on a statistics topic. So take your time, read them carefully, and pause the video now and try them on your own. When you're ready to see if you've got the right hang of it, please press play and I'll guide you through question 1 and question 2, obviously, in turn. So without further ado, let's have a look at this first one. So here we've got a manufacturer who's carried out a survey of the defects in their soft toys. It's found that the probability of a toy having poor stitching is 0.03 and that a toy with poor stitching has a probability of 0.7 of splitting open. A toy without poor stitching, however, only has a probability of 0.02 of splitting open. So what we're asked to do first of all is to draw a tree diagram for this information. So first of all, let's just think about what we're doing. There's two things here. Either it's got poor stitching or not. So we need two branches to begin with. So call them what you like as long as they make more or less sense. So I'm going to say this one's poor stitching. And the bottom branch I'll just call good stitching. And then, depending on if the stitching is poor or not poor or good as I've called it, that will affect the probability of if the toy splits open or not. And understandably, if the stitching's poor, there's a much higher probability of the toy splitting open. So obviously it can either split or not split. And the same, even if it's got good stitching, there's still an outside chance that it could split open. And let's just think about all those poor children who have a toy which looks good but still splits open, and the tears resultant from that nightmare. And so if this brings back any troubling memories from your past where you've had toys that have split open. And I can't seem to spell split because I'm being a numpty. S-P-L-I-T. There we go. So just filling in the details. So if it's got poor stitching, the probability of that is 0.03. And from that we can deduce if the stitching isn't poor, it's binary. So if it's not poor, we can just deem it to be not poor or good, as I've called it. So 1 minus 0.03, the probability of good stitching must be 0.97. Now, it does say here afterwards, a toy with poor stitching has a probability of 0.7 of splitting open. So we need to fill in that value in the correct place. So poor stitching, 0.7 chance of splitting. So that 0.7 goes here. If it's got a 0.7 chance of splitting, that means there's a 1 minus 0.7, in other words a 0.3 chance of it not splitting open. Whereas here, if it is without poor stitching, if the stitching's fine, there's only a probability of 0.02 of it splitting open. So we put 0.02 here. Therefore, of it not splitting, if the stitching's good, will be 1 minus 0.02, which is 0.98. So that's part A done. We've done the tree diagram. For part B, we're asked to find the probability that a randomly chosen soft toy has exactly one of the two defects. Either the stitching's poor or it splits open. So for part B, which I'll do up here because there's a bit more space, as you can see. So we want to work out the probability of poor stitching just put PS, and doesn't split, that's one way it could happen. Or, which is plus, we need to add on the probability that it's good stitching, so that isn't a defect, and the defect is that it does split. So those are the two ways we could have exactly one defect. Defective stitching, not defective with the splitting, plus a probability of non-defective stitching, in other words good stitching, and the defect of it actually splitting open. So and with probability, going back to GCSE even, works as a multiplication essentially. So this one here, probability of poor stitching is just 0.03 for poor stitching, so 0.03, then and multiply the chance it happens not to split anyway, that's going to be 0.3, plus the possibility that the stitching is good, which is 0.97. Most of these toys have good stitching, which is pleasing to know. And so multiply the probability that it happens to unfortunately split anyway, which is 0.02 chance. So once we calculate this, we have to just see what this gives us, and then we round the answer appropriately if needed. So 0.03 times 0.3 for this one, then add on to that 0.97 multiplied by 0.02. And from that we get 71 over 2,500, which I suppose you could leave like that if you wish, or as a decimal, 0.0284. This is three significant figures, that's more than reasonable to leave it like that. So 0.0284. You could have left it as a fraction if you wanted, that also is absolutely fine. So part C next, find the probability that the soft toy has none of the three defects. So a third defect, what's this talking about? It's this information here. So after part B, we're told the manufacturer also finds that the soft toys can become faded with probability 0.05, but this defect doesn't depend on the stitching or if it splits open or not. So if a soft toy was chosen at random, what's the chance it has none of these three defects? So we want the probability that the stitching is good stitching, and doesn't split, and that it doesn't fade. So, like I said before, the and works as multiply, like I did here. So we're going to have three different probabilities multiplied together. So first of all, we'd have to have a toy picked which has good stitching, which is a 0.97 chance. And then, so multiply that by the probability that it does not split. So given that the stitching is good, so we're going along this avenue here, the chance it doesn't split would therefore be 0.98. And then, so multiply yet again, we're after the chance that it does not fade. So we're told here that the chance of it actually fading is 0.05. Therefore, the probability of it not fading will be 1 minus 0.05, which is 0.95. So multiply all those together and round if needed. Let's see what we get here. So 0.97 multiplied by 0.98, then multiply that by 0.95. This gives us 0.903. So we can round that to just 0.903 if we want. So just over 9 out of 10 toys are going to be sold and are going to be absolutely fine. Then for D, we want to have a probability that the soft toy has exactly one of these defects. So this could happen in one of three ways. So we've got 3 different probabilities to add together. So the first scenario is it could be that the stitching is good stitching, and that it doesn't split, and the only defect isn't the stitching, isn't that it splits, but that it does fade. Or, so plus, it's a probability as well that we could have stitching is good still, so the defect isn't the stitching. This time, rather than the defect being that it fades, the defect might be that it does split open. So good stitching, and it splits, and but it doesn't fade. So that's the second option. So first option is the only defect is that it fades. This second scenario is that the only defect is that it splits. The third defect, so the third possibility, is the probability that the defect is the stitching itself. So probability we've got poor stitching, but there's no other defects. So poor stitching, and despite that, it doesn't split. And that it doesn't fade. So here, we're just looking at the defect being the fact that it is poor stitching. So we've got 3 separate ones to add together. So the first one is this. So let's calculate this first of all. So good stitching, 0.97 chance. And, so multiply, doesn't split, 0.98 chance. 98% chance it doesn't split if the stitching is good. And probability that it fades is 0.05. So that's the first of the 3 possible scenarios. So, or we could have it that the stitching is good. So again, still good stitching, 0.97 chance. And despite the stitching being good, it splits. So if it's got good stitching, the chance it splits is 0.02. And then that it doesn't fade. So the chance that it fades is 0.95. So the chance that it fades is 0.95. Therefore, the chance it does not fade is 0.95. So this one here, that scenario, I've just wrote down the calculation for that one. And the final one, we're going to add probability that it's poor stitching. Poor stitching is 0.03 at a chance. And then it doesn't split anyway, luckily. That's a 0.3 chance. And the fact it does not fade. There's a 0.95 chance of it not fading. So that final scenario, I'm going to put in a lovely orange colour. Well, maybe you don't like orange, but I think that's quite a nice colour. So all you need to do is work out this beastly calculation. So just be doubly careful how you press this in. So here we go. The same goes for me. So be careful, Mr. Bailey. So 0.97 times 0.98 multiplied by 0.05 plus 0.97 times 0.02 times 0.95. Got the first two. And finally, 0.03 times 0.3 times 0.95. Press equals and hope. We get 0.07451. So you can round that if you want to 0.0745 or include the 1. It doesn't particularly matter as long as you have an answer that does round to 0.0745 if you gave it 3 significant figures. So 0.0745 is what I'm going to call my answer. 0.0745. 7, 4, 5. And that's the first of a rather large warm-up questions we've done. Next, let's have a look at warm-up question 2. Question 2, as you can see, is a Venn diagram question. So we've got 3 different activities, people that run, swim, cycle, or do some combination of the 3. Even some people do all 3 activities together. So the clue here, we've got 3 activities, we need 3 regions. And because some people take these different exercises together, these circles need to overlap. Not only that, but there needs to be a bit where all 3 circles overlap together, because there are some people that do all 3 activities at the same time. Well, not at the same time, but they do 3 activities. So what we need is 3 circles which overlap in a way similar to this. So my suggestion is to draw something that looks a bit like this. 3 overlapping circles with a big overlap bit in the middle. So what we need to do is we do the biggest overlapping bit first. In fact, that's half a lie. What we should probably do first is label these regions. So I'm going to label one circle R for running. In any order, I'll label another one S for swimming. I'll label the final one C for cycling. So the 25 people that do all 3 will be represented by the region where the R, S and C circles all overlap together, which is this middle section here. So what we need to do first of all is to fill in 25 in this middle bit, because 25 people do all 3 of these activities. So we always do the biggest overlap first. After that, we do the ones that overlap, but just 2 things together. So there's 3 different ones we can do: run and swim, swim and cycle, run and cycle. Do them in any order, as long as you do these overlapping bits before the ones which don't mention any overlapping ones. So we do these ones here at the top last. So I'm going to pick, let's go for 40 running and swimming. So the people that run and swim will have to go in the region where the R circle and the S circle for swim overlap together. Now hopefully you can see it's going to be in this region here. I'm colouring in red. This red bit in the middle is where runners and swimmers coincide. And there needs to be 40 people in total in this region. We've got 25 people so far here, so we need an extra 15. 40 take 25, we need an extra 15 here. 15 plus 25 gives 40, so that checks out correctly. Next, I'm going to do the swimming and cycling people. 40 swim and cycle. So these people need to go in the bit where the S circle for swimming overlaps with the C circle for cycling. So it's going to be this region here I'm going to do in blue. Bit wonky there, but hopefully you take the point. So 30 people in total need to go in this blue section. I've got 25 here so far, so I need an extra 5 in this bit. The final overlap bit is the runners and cyclers. So 35 people need to go in the region where the R circle overlaps with the S circle. And so where R and S overlap is going to be, sorry, R and C is going to be this bit here. Oops. I've gone over the 15, which wasn't too wise, so there we go. So 25 people need to be in this bit. I've got 35 need to be in this bit. I've got 25 so far, so we need an extra 10 people in this region. So that 10 plus 25 gives us the 35 we need. Once you've done that, you've actually done the hard bit. The rest is just filling in the numbers to make it add up correctly. So what we've got here is, it says 65 people need to be running. So the running circle so far, this bit here, there's 10 plus 25 plus 15. That's a total of 50 so far in this R circle. We need 65, so this number needs to be the extra 15 to make these here add up to 65. We're told 48 people swim. This swimming circle, the S, 15 plus 25 is 40, plus 5 is 45. We need 48 people that swim. 48 minus 45 tells us this bit here needs to be the extra 3. And lastly, for the cycling people, 60 people cycle. So the C circle needs to total 60. So far it totals 10 plus 25 plus 5, which is 40. So we need an extra 60 minus 40, which is 20 here. At this stage, it's tempting to think we've finished. But actually, if you add up all these values, you need to check to see if it totals 100, because you're told there's 100 people altogether. So what we need to do here is to add all these up. So we've got 15 plus 15 plus 25 plus 10. So that's the R circle. Then we've got a 3 and a 5 here, so plus 3 and plus 5. And finally, this 20. That gives a total of 93, but the question clearly says that there's 100 people surveyed. So it could be, of course, that maybe they don't run, swim or cycle. So to be honest, I'd imagine there'd be more than 7 out of 100 people that do no exercise. So there are going to be some people that don't go into any activity circle. 100 people in total, 93 people here do some form of exercise. That tells us that 100 minus 93, which of course is 7, don't do any of these three activities. So we put 7 outside of all circles, but within the rectangle. That Venn diagram is now fully complete. So never forget the outside number. So that's part A. Based off these results, the rest is actually much easier. So part B, what's the probability from this survey that a randomly selected person takes none of these types of exercise? Well, 7 people out of 100 don't take any forms of these exercise. So that's just simply 7 over 100. Part C, what's the probability that this person chosen at random swims but does not run? So how many people swim yet don't run at all? Well, we've got here, it says 48 people swim, but we want the swimmers that don't run. So the running swimmers are these 15 and 25, which is 40. The people that swim but don't run are just these 3 plus 5, which is 8 of them. So that gives us a total of 8 over 100, which if you wish, you can simplify, or you can leave it as 8 over 100, that's fine as well. D. What's the chance that the person chosen at random takes at least 2 of these types of exercise? So if we take at least 2, that's the people that run and swim and cycle, run and cycle, or do all 3. So essentially it's just the people that reside in any one of these overlapping regions. So if the overlaps are these 4 middle numbers here, the 10, the 25, the 15 and the 5. Add these together and we've got it. So 15 plus 25 is 40, plus 10 is 50, plus another 5, that gives us 55. Now, this one's slightly harder, but I'll just try and guide you through. So Jason is a member of this above group. So Jason's one of these 100 people. We're told that Jason runs. So given that he runs, find the probability that he swims but does not cycle. So we know he runs. So how many people run? Well, based off the fact we're told that he runs, we know that he's not going to do anything which is outside of this R circle. So at this stage here, we can ignore the 7. He's not going to be one of those 3 people. He's not going to be one of these 5. And he's certainly not going to be someone that just cycles. So he's going to have to live somewhere in this R circle. So how many people run, essentially? 15 plus 15 is 30, plus 10 is 40, plus 25 is 65. So Jason is 1 out of 65 runners, which of course you could have worked out by just looking here. So what's the probability that he swims but does not cycle? So if he's swimming but not cycling, we want to avoid anyone in this C circle. So if he's not cycling, We don't want this circle at all. So if he swims, but does not cycle, he must be one of these 15 people. So he must be one of the 15 out of the 65 runners that runs and swims, yet doesn't do all three. So that's question 2 done, and that's the full warm-up. Let's have a look now at the main new part of today's topic. So measuring correlation. So let's just recap on what correlation is first of all. So remembering and recalling from GCSE, correlation is just a measure of the strength and type, positive or negative correlation can be, of the linear relationship between two variables. In fancy language, two related variables are called bivariate data. Bi as in two, variate as in variables. A common measure of correlation is known as the product moment correlation coefficient, which is called PMCC for short. So again, like at GCSE level, the PMCC, usually denoted by the letter R, it can take any real value between -1 and 1. So if you remember from GCSE, correlation is measured in between -1 and 1. So if R is 1, there's perfect positive linear correlation. So all data points lie perfectly on a regression line. Now, regression line is just a fancy way of saying it's a calculated line of best fit, and it's calculated using this PMCC. And if it's positive correlation, the gradient of the line of best fit, the regression line, will have a positive gradient. The other option, or one of the other options, if R is -1, that means there's perfect negative linear correlation. All data points would lie perfectly on a regression line with a negative gradient at that time. If, however, though, if R is 0, or so close to it it may as well be 0, there's essentially no linear correlation between the two variables. So that means if R is 0 or very close to it, there's no meaningful linear relationship between the two things. However, it could be that there is a relationship between them that just so happens to be not linear. So it could be an exponential relationship, it could be quadratic, it could be reciprocal. But importantly, today we're going to be focusing on exponential relationships. That's what we saw last section, and that's also what we're going to be looking at here as well. So let's just have a look at what R might look like roughly for different scatter graphs. So that one there, all points lie on a straight line. So that regression line goes to all points, so it's perfect correlation with a negative gradient. R is -1. Perfect negative correlation. Here, clearly the points all are fairly close to a negative gradient straight line. So the line of regression is negative gradient. R is -0.8. So it's fairly close to -1, but it's not -1 because it's not quite perfect. Some of these points are slightly away from the line. This one here, the points are all over the place. There's no meaningful correlation, no linear correlation anyway, so R is 0. On the other hand, if the points tend to be going sort of upwards, that's a very weak positive correlation. The line of best fit does go up, this regression line, but it's not as though all the points are very close to it. So it's a weak positive correlation, so positive 0.3. Whereas if it were perfect positive correlation, all points would lie on the same straight line, which would have a positive gradient of R equals 1. Like I mentioned briefly earlier, the good news is the calculator can do all this calculation for us with no guesswork, no needing to use a ruler to measure it and guess whereabouts it goes. The calculator really saves the day here. So I'm going to guide you through now how this can be calculated, the strength of correlation and the line of best fit itself using a Classwiz. So, step by step. First of all, I would always recommend the Casio Classwiz. If you're watching this video in several years' time, maybe it'll be a different calculator, but I will imagine any calculator from 2022 and beyond will be able to calculate the PMCC for you and the equation of regression lines. So using the Classwiz in particular, which is one of these things here, Your first step is, well, apart from switching it on, of course, press menu and then 6 to get into statistics mode. So on my virtual one here, what we're going to do is press menu. So watch carefully. So I'm going to press menu and then scroll to 6. So you can either toggle to 6 or just press 6, then equals, or just option 6. After doing that, the second step, there's option 6. What we need to do next is press number 2 for y equals a plus bx. This essentially is y equals mx plus c with different letters and a different order. So this is fairly easy to remember because you're wanting it to be a straight line relationship that you're going to be coding. So on mine, just press option 2, then you get this here, a table of values for x and y. So now you've got your table of values, you just enter values for x and y into the table. It's normally relatively obvious which is x and which is y. If you put them in the wrong order, it won't affect the PMCC calculation, it won't affect ever the value you get for the strength of correlation, but it would affect the equation of the regression line. So if a question asks you to calculate PMCC, don't be too worried about which is x and which is y. So I'm going to just make up some numbers now to go into the table. So like I said earlier, if the regression is positive, if a correlation is positive, it will be a value greater than 0, and if a correlation is strong, the correlation coefficient will be close to 1. So I'm going to make up some data which is positively correlated very strongly. So I'm just going to type in x is 1, 2, 3, 4, and 5. So if x is 1, 2, 3, 4, 5, I'm going to imagine that y is going up almost exactly the same, perfectly, with x. So x is 1, y is 1, x is 2, y is 2, 3 and 3, 4 and 4. I'm going to deliberately mess it up slightly. I'm going to put 5 and then 6. So the last point doesn't quite go on the same line. So input the data, then do what? So what's step 4? Once you put the data in, step 4 is we're now going to press the option button, which is in the top left there, and then press 4 for regression calc. So on mine, press OPTN and then option 4. So as you can see here, R stands for the correlation, 0.986, so about 0.99, almost perfect. Like you saw with the numbers, the coordinates were going up in a perfectly straight line. I just deliberately fudged the last one so it wouldn't be perfect. So that hopefully will make sense to you, but it's positive and close to 1 for very strong correlation. So what do we do with A and B? Well, simply, it comes to step 5. You record the values for A, B, and the PMCC. So in our case, it says y equals a plus bx. So the equation of the regression line, so I always think of it in terms of y equals mx plus c, linking it back to GCSE. So for one I've just done here, b is the gradient because it's the coefficient of x, so b is 1.2. So we'd have y equals 1.2x, and then a was roughly, oh no, exactly in fact, minus 0.4. So 1.2x minus 0.4 would be the equation of the regression line for those points we drew. And of course record down that r equals 0.9, what was it, I've forgotten? 0.986. Very strong correlation. And that's all there is to it. The calculator does the legwork. You don't need to go out of your way to show the working. The examiner knows nowadays that if a student is studious and well trained with their calculator, that they've generated these values from the calculator. You don't need to just make up formulas or just say, I'm using my calculator to do this. Just write down your numbers, that suffices. Don't waste your time if a calculator can do the legwork for you. Let's now have a look at some examples using this. So worked example 1, From the large data set, the daily mean wind speed, W knots, and the daily maximum gust, G knots, were recorded for the first 10 days in September in Herne in 1987. First of all, state the meaning of NA in the table above. Well, NA, in any sort of English-speaking world, NA literally stands for not applicable. So if G is not applicable, that essentially means we had no data for G on day 8 and day 9 of that month. So for part A, something along the lines of this will do. So NA just means no data for G was available for these days. So therefore, because to plot the regression line, we need both sets of data for each point. We need co-ordinates, not just an ordinate. These 2 days we can't really use because G is missing. So day 8 and day 9, we can't work out those coordinates. So part B, like it says, calculate the PMCC for the remaining 8 days. So we scribble off 8 and 9. We're going to input W and G for these 8 days. So let's do this. So again, just showing you what the steps are. Press menu, option 6, then we press option 2 for y equals a plus bx, which will get us a linear approximation. So values of x, like I've said, the order doesn't matter. All we need is to work out the PMCC. So for x, I'm going to use w. So values for w, gone a bit too far over. I've got 4 and 4, so 4 equals, and 4 equals 8, press equals, 7, press equals, 12 and 12, 12 and 12, 3, and like I said, we're ignoring these 2 and going straight to 10. Once you typed those in, we toggle to the right, so press this button here and go back up, and then what we're going to do is type in the corresponding values for the gust. So the first one is 13, then we have 12, and then 19 again, 23, 33, 37, 10, ignore those 2, and finally the one we use is 23. So we've typed in all the data. The next step, do you remember what it was? Well, we press OPTN for option and number 4 for regression calculation. So we then record the value of R which we get. So the value of R here for regression is 0.9533. So for B, R equals 0.9533. So not only is that positive, it's very close to 1, which denotes a very strong linear relationship, which leads us nicely onto part C. So with reference to the answer from B, this here, comment on the suitability of a linear regression model for these data. So for part C, if you want to write something along the lines of, because R is very close to 1, this would strongly suggest that a linear regression model is suitable for these data. So I've been slightly conservative in how I've worded that. I've used the word suggest rather than definitely, because there's always a small chance that this just happens to be a fluke. It could be that it's not a linear regression model, just happens that the sample we've taken misleadingly gives that impression. That's actually going to be our next session, how we can know for sure, or close to sure, if it truly is a linear model or if a linear model isn't actually appropriate. But here, for R being 0.9533, I'd be very, very confident that a linear model does work and is appropriate. Let's have a look at another worked example which I've made up myself based on an ongoing situation we've got still in the world, which I'm sorry to say is COVID. So this data I found myself from the lovely website, possibly my favourite website ever, Wikipedia. It's better than you think. So in the first quarter of year 2020, the UK government attempted to model the emerging COVID-19 pandemic in terms of rising cases. They wanted to find out what was going on. So in the table below, it shows days after 27th of February 2020, which are called D, of the total cases up to that point in time, C for cases. So it's called COVID-19 because it first emerged in China in 2019, but it only started taking off and gathering momentum mid to late February. So there was like 1 or 2 cases, wasn't really moving, then it just ended up exploding. So at this point, and soon after this was the first lockdown, the government would have been thinking, what on earth is going on? How can we predict what's going to be coming up in the next few days? So someone probably did think, I wonder if this is exponential. So the data could be coded using x equals d. So there's no meaningful coding for x, we just change the letter. But y does have coding. We've transformed it into a logarithmic relationship. So we're going to call log c y. So we're going to take c and take log of those. So first of all, we need to complete the table for the values of log of c. So all these values here, we're just going to log them. So for the first one, 19, do log base 10 of 19. So go back to menu option 1 to get into the normal mode. So log base 10 of 19. I'm going to give these figures to 4 significant figures to make sure we're not rounding too prematurely. In fact, no, I'm going to go to 4 decimal places. Scrap that. So 1.2788. Next, log of 23, so toggle back, 23, 1.3617. Log of 35 next, 1.5441. Then log 40. Do this yourself at home as well if you're watching. Make sure you can actually compute these as well and can do this at the same time as me so it truly goes in to help understanding. 1.6021. Then log of 51, not too many more to do now. Log 51 gives us 1.7076. Log 85, 1.9294. Log 114, 2.0569. And the last one to calculate, log of 160. That gives us 2.2041. So that's part A done. We've done the table. So part B, you need to calculate the product, moment, correlation, coefficient, and the equation of the regression line for the coded data. So let's have a think about part B next. So again, this is where the calculator comes into play yet again. So using these values, we're going to put them in and see if we can model them as a linear relationship. How do we do that? Need to remember, you press menu, option 6. Number 2, to model as a straight line. So the value for x, it says here y is going to be log c. So the values for y are going to be 1.2788, and these numbers in red. Now x, let's just move along, is going to be d, days after 27th of Feb. So d just goes from 1, 2, 3, 4 all the way up to 8. So that's all we need to do for x. Just going to go 1, 2, 3, 4, 5, 6, 7, 8. Dead easy. We're not typing in c, we're going to do log c. So 1, 2, 3, 4, 5, 6, 7, and 8. Press equals, then toggle right and up and fill in the corresponding values. So for the first day, after the 27th, the 28th of February, log of the case numbers was 1.2788. Next one, 1.3617. Then 1.5441. 1.6021. 1.7076. 1.9294, 2.0569, and lastly 2.2041. Press equals, then we press OPTN and option 4 to get the analysis of the data. So option 4 for regression calculation. And as I say, this I just researched myself and I was amazed to see that R was 0.993. That's almost flawlessly perfect correlation. R equals 0.993. So for B, the PMCC equals 0.993. That's freakishly high. It almost perfectly fits an exponential model. So we can say, both literally and mathematically, at the beginning of the case of COVID, the cases were rising exponentially. It's an often overused word, exponentially, but this truly is. And the equation of the line of best fit, we can work out as well. So y equals bx plus a. So b, I'm going to give to 4 decimal places. So b is 0.1335. So y equals 0.1335x in terms of regression line. And the y-axis intercept, as it were, the a, is 1.1098. So plus 1.1098. So the product moment correlation coefficient is this, and the equation of the regression line is this. So for C, with reference to answer to B, state whether an exponential model of the form y equals an to the x is a good fit for the data. Well, like I've just said, really, it's almost too good. This PMCC is really close to 1, which would suggest that an exponential relation is an excellent fit. So for C, we want to write something along these lines, because R is 0.993, which is approximately equal to 1. It's so close to it. This would suggest or imply that y equals an to the x fits the data very well indeed. Part D is actually determining the values of a and n, giving answers to 2 decimal places. So I'm just going to take here the regression line, which was y equals 0.1335x plus 1.1098. So I'm just going to have that in mind, okay? So what we're saying here is it needs to fit a model of the form y equals an to the x. Okay, so y equals an to the x. Let's see if we can just manipulate this slightly. So I'm going to put the working over here. This goes back to the first lesson on this topic. We take logs of both sides. So we have log y equals log of a n to the x. So this is the log of a product. It's log a times n to the x. So we can split the log product using the laws of logs into 2 separate logs. So that becomes log of a plus the log of n to the power x. And then you've got the log of something to a power. You can drop the power to the front. So log y is log a plus x log n. So I'm going to write this underneath here so we can compare and contrast which variable relates to which thing. So log y, now we've got the x stuff first, so I'm going to put this as log n times x. X log n is the same as log n times x. Then plus log a. So now we can compare and see what bit matches up to what value. So like we said, y is going to be coded as log c. So this thing here is going to be log of the case numbers. Log c, log y, c, y. So our y-axis is going to be C. Too many letters, you might be thinking, but as long as you can marry up and see what matches to what, we can fill in the details after. Next, we can see that the coefficient of x, the gradient if you like, of the regression line must relate to log n, because that's in front of the x here, just as 0.1335 is in front of the x in the top equation. So we can highlight those and match them up. Finally, we can match up that plus log a must relate to the 1.1098. So we can work out n by saying that log n must equal 0.1335. So therefore n, opposite of taking logs of n, we undo that by raising it to the power 10, this value here. So n will be 10 to the power of 0.1335. And let's give that answer to 3 significant figures. So 10 to the power 0.1335. That gives us 1.36. So n is 1.36. In a similar way, we can now work out what a is, because we're told that log a, well, we can see that log a is 1.1098. So log a, 1.1098. So therefore, a itself is going to be 10 to the power of 1.1098. So just change this, 1.1098. That gives us to 3 significant figures, 12.9. Okay, so filling this in, not that the question asks us to. If a is 1.36, sorry, if a is 12.9 and n is 1.36, then we can actually fill in and realize what the equation is going to be. So C, for total recorded cases, that's log C. So log C is going to relate to the type log Y. So y-axis is going to be our C. We can see that C must be a times n to the power x. A is 12.9. I'm going to multiply that by n, 1.36 to the power x. Now, even though the question doesn't ask that, I'm going to show you just how well this exponential model fits these data. So I'm going to come back to do part E in a moment. Part D we've done, we've got the values of a and n here, but just looking at this, I plotted it on Desmos. So if I just take here our relationship that the C case numbers should be 12.9 times 1.36 to the power number of days, I'm just going to show you how closely it seems to fit. So here we go. So we've got here the cases plotted. So you can see 119, 223. So it's rising in a curve. And like I've said here, that's what I think it might well look like. C equals 12.9 times 1.36 to the power x. So the y-axis is case numbers. That's C. And x, number of days after 27th of Feb. So if you were to plot it on Desmos, you get something that looks a bit like this. Now that red line very closely matches these points. It's not perfect, it very seldom is, but it's a very, very good fit of an exponential curve. So that's a real life application of these exponential modelling questions. You can see actually that's surprisingly good in terms of an approximation. So just going back here for a moment, we need to give a reason why this model may need revising as the number of days from 27th of February increases even further. This is a fairly standard one marker, okay, so it's just applying a bit of common sense. So why might this model need revising or changing as the number of days increases? Well, I think the easiest thing to say is if you're reading data beyond that which the data is taken for, that's called extrapolating. If you extrapolate data, it's always a risky business. So probably the easiest thing to say is something along the lines of you'd be extrapolating beyond the known data range. So you'd be guessing, which is a dangerous game to play. That would be worthy of a mark. If you've got a bit more of know-how about COVID and you can remember what's been and gone in terms of how it panned out, you could also say a bit more stuff in terms of context. So another example could be, obviously there's only a finite number of people the virus can infect. As X goes on, 1.36 to the power, say, 100 days times 12.9, you're talking millions upon millions of people. Of course, C can't be higher than, say, 10 billion. There's not that many people on the planet, so eventually this will just become ridiculous. It can't carry on forever. Another reason why not only is there only a finite number of people as a valid reason, but of course, as you can remember no doubt, the government reacted. So this data doesn't take into account science, for example vaccines, which will make the case numbers taper off and slow down. Also as well, the rate would eventually slow as social measures, for example lockdowns, were brought in. This model doesn't take that into account. So in the future, it starts exponential, goes really high, but then it will even out. And eventually, fingers crossed, we'll learn to live with this very, very horrible thing. So there you have it. That's a practical application of what we're doing in this chapter. So now it is over to you to try some questions on your own. So here's the suggested exercises I want you to have a go. So if you turn to page 6, all of exercise 1b of this stats and mechanics exercise. It's relatively, well, I was going to say easy. It's accessible. Once you do a few, you'll get the hang of it. So do a whole chapter. These questions do come up fairly regularly. They're well worth practicing. And you know the drill by now. If you get stuck, please do leave a comment in the comment section. Like and subscribe to the video if you could. That's really nice of you to do so. And I hope you found some of this useful. Good luck in your exams, good luck in life, and you know where to find me. So stay in touch and you'll hear from me again soon. So from me, it's goodbye for now, everybody.